PHYS. Where's the works? These cylinders. This one? I enclosed here in the inner half of the thing.
Yeah. No, because it's hollow. I can't think about it for some reason. I don't know.
Okay. Inner cylinder has radius of A and carries a current total of.
Like the inside is fine, not the inside.
So you know how to find this one, right?
Yeah. I mean, that's just how
Yeah, but this one. This is A. This is B, or is this C? There's B. Yeah, that's B, that's C. That's C, and I assume this is half the distance. Yeah. So. I enclosed in here. And we know that the current is D. What's the current that's flowing through? What would you do it in terms of I1 and I2? I guess. This is I2. Okay, and we want to find this. So we're assuming that the current is, the flow of current is the same anywhere. So this is going to have the same current as this. So the current is going to be distributed over the entire. So the flow of charge is distributed over the entire cross-section area. So the area of this thing, I mean, you can do it multiple ways. We either define a quantity that's current over the cross-sectional area. If you find the area.
I have a question.
Yeah.
It is a very stupid question, but why is it not half of this current?
Why is it what?
Why is it not half of the current?
Yeah.
Why is it not half of the current? Because this area is not half of this entire area.
Oh, really? It doesn't say that it's.
It is in the middle, but that doesn't mean the area is the same. So what's the area of this entire? Let's find. Well, we're gonna have to find it, so we'll see why. We're gonna have to find the area of this thing all around, which is the area of the bigger circle minus the area of the smaller circle, right? Mm-hmm. So that's just going to be, what's the area of the circle? It's going to be pi c squared, right? Minus
pi squared?
Minus pi b squared. Try to read that, right? This is.
Oh, C.
Okay.
Which c is the radius.
Yeah.
This is a. That's called a total. So a half, it's not really half, we'll just call it a half, is equal to pi d squared minus pi d squared, where d is the radius of this dotted circle.
Oh. A half is?
A half is the area of this outer circle minus the area of this circle.
How did you write it? What is
D? D. So we're saying that this radius is A. Oh, well, that's not relevant. This radius is B. This radius is D.
Oh.
And this radius is C.
Okay.
Yeah. The area of this annulus, which is the area of this outer circle minus the area of this inner circle, which leads to this area. So the ratio is smaller area I just cancel out. Squared minus b squared. C squared. C squared. That's the ratio of areas. How much of this area is with respect to this red one.
Why do you need the ratio?
Because the current, we're assuming that the current is distributed. I mean, the flow is equal throughout the entire thing. And we're saying that the total flow of charges, total current, is equal to I1. But we don't care about this current that's outside. We don't care about the current that's in this black region. We only want it. So that's we. So the ratios of area is going to be the same as the ratios of current. So I enclosed is going to be equal to I1 over multiplied by that ratio. 2 squared minus c squared over c squared minus y squared plus or minus, in this case, because they're I'm just going to put this here. Technically, it's direction wise. In this case, we subtract them because one is in the opposite direction. That's easy.
I mean, I didn't do the homework, so I don't know what kind of questions that are.
The question was just find the magnetic.
I remember it was from whiteboard.
Yeah, it was pretty much the same thing. Find the magnetic field at this point here or something, which is half the distance. So that's your item close, and then the integral DL, kind of like us as well. Go to item close. D is constant. Integral dl is L equal to U naught I enclosed. Then we solve for B. B is equal to mu naught I enclosed over L.
And L is the arc length, or like the area.
The entire length. L is the entire length of the thing because we're assuming this integral is enclosed. So enclosed integral means integral of the entire surface from the beginning point back to the beginning point.
So is it 2 pi d, right?
Yeah, 2 pi d, yes.
D, okay.
This is your L. L is equal to 2 pi d. D. It's not a D.
Yes.
Did it work? Yeah, let me didn't try it. What else do they have? What else do we have in this homework? Two infinite sheets. Two infinite sheets looks fun.
Yeah, I'm sorry, I'm stuck on the first one.
It's pretty similar to Gauss's law.
Yeah, I can.
A lot similar.
I hope that we'll never see them again. But
Except it's like Gauss's law, you have to think more about the integration. Like Gauss's law, you could just simplify it usually to just E dot D, or like E times A.
This one came too, if it's symmetric.
But you're thinking about the length and not the area.
Yeah. But if it's symmetric, you can still simplify it into B times L instead of E times A. It amounts to the same thing.
So you're gonna give us a problem where it's like a small circle and then a bigger circle. You know what I'm talking about?
Small circle and bigger circle.
A small semicircle. So like half, it looks like this. And then, or actually, no, sorry. Like that. And this is like all just current going back here. Remember that example?
we never talked about
I mean, we didn't have it in class.
Small semicircle.
So you just find, I don't know. I just remember doing that problem. It looks like that, yeah.
I think I know what you're talking about, but for some reason.
Is it Ampere's law or?
No.
Is it a different unit?
You have to find the magnetic field of something.
Yeah.
This is the current, right?
Yeah.
Yeah, you have to find the magnetic field of the loop.
Right.
Did we talk about the magnetic field of the loop?
Maybe not.
I think the pre-lectures did talk about it a little bit, but we don't focus on it for some reason, but we can do something like it. It was the same lecture where they introduced the magnetic field formula. Well, these are not unlocked for me because I don't really do them. Current of a loop, yeah, this one. This one's what I'm talking about. But I guess that's not necessary here. This is the one that's necessary is when you're at your center. So z denotes the z-axis. So at your center, z is going to be 0. And that integral is going to simplify to mu naught I over 2r. So we can prove that. I think it's pretty easy to prove. You just need the basic form of PHYS221 law, which is mu naught. PHYS221 law is this one. So it's mu naught I ds cross r over 4 pi r squared. ds cross r. I can never remember this. It's an area vector in the direction of r squared. So I is your current, ds is r. So
I don't think there was an r there.
There's not an r there.
There's only the r squared. I don't think there's no. I don't think that's there.
Yeah, I think you're right. So that's dB, the magnetic field here from a small segment, ds. ds is for small segment. And we want to sum up b is equal to the integral. Let's just do it for a simple loop before we get into this. So if we do it for a simple loop, I don't think you can prove this with Ampere's law. It's not symmetric.
So that's for PHYS221 though?
Huh?
That's for PHYS221 law?
Yeah, that's 3 by PHYS221 law. You get to this new one.
Okay.
So dB creates a small magnetic field ds creates a small magnetic field dB, and we just want to sum them up all. So that's going to be the integral ds r squared. We don't care about the cross product because it's going to be perpendicular because we're not working outside the dimension of the plane. Right?
Right.
Because ds is going to create, if the current's flowing in this direction, ds is going to create a magnetic field going outside, right? Which is perpendicular, so we don't really care about that. It's fine.
Right.
Oh no, that's actually the cross product. We'll still don't care about the cross product, but that's a different cross product. My bad. That's the cross product between your segment and your radius. Your radius is always perpendicular to your segment. It's not small. Yeah, still. So that's equal to, since s is equal to r theta, that's equal to mu naught over 4 pi I. So ds is equal to r d theta because r is constant, radius is the same. So that's just going to be r d theta over r squared. One of the r's cancels with the other r. And we're taking the enclosed integral. That means throughout the entire circle, the enclosed integral goes from 0. Theta goes from 0 to 2 pi. To 2 pi. So that's the integral from 0 to 2 pi of mu naught I d theta over 4 pi r, which is equal to 2 pi times this thing times mu naught over 4 pi r. Pi cancels out with pi, 2, 4, which is equal to, I have an I somewhere, mu naught I over 2r. Is that correct? That should be the result that they got. and this is for the z-axis, but we were only working in a dimensional plane. So an example on a problem like this would be, so this is the equation that we just derived, magnetic field at the center of a loop is equal to mu naught I over 2r. So let's start with a simple example. We have just a loop, nothing really else. So I is equal to 5 amps, and the radius is equal to 2 meters. Don't even want anything other than the standard SI units. So the magnetic field at the center, what's the direction of the magnetic field at the center? Outside, right? Is equal to mu naught I over 2r, which is equal to 2 pi times 10 to the negative 7. I is just 5 amps over 4. And that's 2.5 pi 10 to the negative 7 Tesla. That's a simple example. Good. All right. Now to do yours. Oops. Give me a second. This is really annoying. Okay. So your example, what do you want your radii to be? 3?
Sure.
Centimeters. 8. Doesn't really matter. I is equal to 5 amps. You find the magnetic field at the center. So that's the magnetic field at the center. How do we find it? We'll consider each segment on its own. Let's call this, start with this segment. Then we'll do this segment. We'll do this segment. And then we'll do this segment. So the current's flowing this way. Right? So what's the direction of the magnetic field at the center? Okay. In center. From the red one, what's it going to be?
Just 3.
Just 3. So this is your equation. Just going to write it here for reference. Just mu naught. Mu naught times 5 over 2 times 3 plus negative 2. What about this segment? What's the magnetic field here from this segment? 0.
Yeah.
Why 0?
Because it's parallel, not parallel. Well, the radius, well, because it's 0.
It's parallel, yeah. Because I mean, it's not on the same line that it's generating magnetic field. And technically, it is parallel.
Like the radius vector would be parallel.
Right. The radius vector would be parallel. Remember how last time we found the radius vector? R is parallel to the direction of the current, anti-parallel to the direction of the current. So that's plus 0. Plus mu naught.
You guys just say it's 0 whenever you feel like it's not the correct way.
No. Well, no. This line is not going to generate a magnetic field here. It's not, I mean, if you have an infinite line, I guess I don't know how you're going to have an infinite line with a dot here. But I mean, if you have a really, really long line that's carrying current, you're not going to have a magnetic field. Remember last time it was. I mean, the thing that we just used was mu naught. What was it? As a works long thing, I ds cross r over 2 pi r squared, I think. So that's dB. Right? Right? So this is so if you're pointed here, your radius vector is in that direction. This is r hat. Okay? And this distance is your r. In this case, this is your radius vector. Hat. It's pointing in that direction. Right? For all these segments, it's going to be pointing in that direction. From here From here, this segment here is going to be pointing in this direction. This segment here is going to be pointing in that direction. This segment in that direction. They're all going to be pointing in that direction. So ds, which is this segment here, that's the direction of this ds. And this is dr, or r hat. ds across dr is going to be 0 because they're parallel. There's not going to be any magnetic field. Well, this is the AT example, so, but I think I have an idea. Oh, this is 8.
No.
Yeah.
Yeah.
Times 2. No.
So it's 2 times 2.
2. Yeah, 2 times 8.
Yeah. It's out of order for sure.
Okay, how about this? One. Just call this R2 is equal to years. 1 is equal to whatever, 20 amps. R2 is equal to 24 amps. Find the x at the center. Yes.
Directionally correct.
I don't care. It doesn't matter. There you go.
I mean, it does.
What?
It kind of does.
It does. I mean, that's not quite the problem. So yeah, here's your direction of the current. What's the point? So let's have them as colors. This is your first one. This is your second one. Okay. What's the direction field from the first one? What's the direction of the field from the second one? Well, I guess I need to explain what's actually happening. This is in. So let's have axes. This is your x-axis. This is your y-axis, and this is your z, which is coming out of the plane. Okay, the red one, red is in XZ plane, and green is in ZY. We can add another one if you guys want. Let's not complicate it too much. So what's the directions of each one?
Wait,
I can do directions. Yourself more.
wait, but that's good for BX, though. We just need to solve for one then.
Yeah, actually, you're gonna have to solve for one. It's not a good idea. It's too easy. B.
Thanks.
There you go. And direction, of course. You still have to find the direction.
Still not that difficult.
Okay. Hi. Yeah.
Do you just find all of them and then add together?
Well,
What else would you do? Yeah, you just find each component and add them together. I guess we should have made this at an angle instead. It would have been harder. That's fine. We'll find
wait,
out.
what do you mean?
I mean, one of the loops at an angle. I mean, just practice angles. Not really hard. They're just more complicated. But yeah, just do this. Let's just do this quick because I can find some more problems. I have a book of problems here. You want to take a look at it?
Sure.
Ooh,
Whoa.
Arabic.
It's not.
Damn.
Okay, so
Oh yeah, you're right. From here to here.
Wait, is this handwritten?
yes.
Was it difficult to
It's not
learn?
mine, of course.
Oh, it's not yours. Okay.
Oh, okay.
Not my handwriting. I'll swear.
Yeah, I think your handwriting is not very nice.
I know.
Sorry.
No, I know.
Well, maybe it's nice in Arabic.
I'm proud of it.
That's not.
So, magnetic field, let's call it 1 is equal to, do we need to solve this?
What? No.
Is it hard?
No. Sorry.
Sorry.
You just find from one little bit you're familiar with, and then you add them. Yeah.
I'd want to get something that's not so conventional, but I don't know if you guys would just like it. I mean, it's not really hard, but it's just. You didn't talk about AC current yet, right?
No.
Leave that for later. Do.
Wait, does the book also go from it to left? It does? First. So this is the beginning?
Yes,
Oh, so cool.
why is that unexpected, though? Why is that so unexpected?
I guess it wouldn't make sense if it was the other way. Still, I don't know. You also write with the opposite. No, I'm kidding.
Yeah, you need to left. No, I'm just kidding.
I try and write in the Arabic classes.
Who?
Bashar?
Whose classes is it?
I don't know.
Is it Freddy's?
I don't know. I hope no. Oh man.
You
I'm not
don't
gonna go. Yeah, I do.
I used to know how to write my name.
Yeah, I have my name written in Arabic.
Nice. Actually, it wasn't even my name, it was my nickname. Like 3 letters.
Okay,
But I wrote it backwards. Just because I was so used to writing from left to right. I still wrote it backwards. Comes right in. That's right. I'm gonna read it again.
okay. First one is this.
I think my handwriting in my right hand is better than yours. Normal.
Oh no, where are my papers? There was a problem if we didn't finish last time, so I just want to finish that first. But I think I lost my papers.
Yeah, no.
So, there they are. Nope, that's not them.
Oh my god, it's in the area.
Did you write something?
With my left hand.
Oh no, we're just trying to write it.
We don't write with our left hand. We don't.
No, I'm just like my name.
It's not necessarily true. But I mean, one cool thing is that we have our start button in Windows on that corner. It is actually. I'm not even joking. It actually is true. Which some people find cool for some reason. I don't know why.
So cool.
Why is it cool?
Because
It's just like the entire world inverted.
it's very different.
Okay. We didn't do this, did we?
No.
Whoa. It's exciting. Why are you so excited about chemistry?
Okay, so You remember physics 1?
No.
No.
Yeah.
So remember this quantity lambda is equal to Q over L, right?
Yes.
That's how much charge we have in a unit length, right?
Yes.
We can have lambda for a bunch of different stuff. For example, lambda m, how much mass we have in a unit length.
Okay.
We did this in physics 1, if you remember, when you had to calculate the length.
Oh, yeah. Inertia.
Inertia, moment of inertia.
Mhm.
So we're just going to say that the segment AB.
Oh, I know what you're going to ask. Right.
What's up?
Sorry.
What's up? Has lambda m is equal to 0.1 grams per meters. Okay?
Mhm.
This is exciting.
And okay, that's all we know. Okay, so
What do you
let's
ask?
call this distance d, and we want to know if we have this current that's flowing through. We want to know at what distance does this wire or this segment, it's free to move, on width, and we are assuming that the current passes through it also. At what distance does it stop moving? At what distance is it in equilibrium?
It's so cool.
I didn't understand the question.
Hold on, wait. Can we not do that because we haven't done inductors yet?
Inductors.
Oh, no, never mind.
Okay, so let me just repeat the question.
So those are touching right there.
Those?
Yeah.
Yeah, they're touching.
Okay.
No, these are touching. I'm just drawing them like this because they're free to move.
Got it.
What's
So you have
the
this one.
original-
The question is that you have this configuration. You have a current flowing through here. Okay. Okay. We're assuming that this length is really long compared to this one. Otherwise, it won't be very accurate. You're going to get a close result anyway. Anyway, you have current flowing here. Okay.
Mhm.
And you have this segment that's free to move on these rails. You can assume that these are rails. Okay. It's free to move. This thing has a linear mass density of 0.1 grams per meters. That means for every meter length of this thing, it's going to have a mass of 0.1 grams. Okay? When current flows through here, something happens such that this thing becomes in equilibrium and stops in place at a certain distance d away from this wire. What is that distance?
Whoa. Hold on.
We don't have anything to find.
You know the current and you know linear mass density.
Me? Okay. So, you know what? Wait, no, hold on.
What? Not enough information?
No, not that.
Yeah, we read the answer like this.
Not enough information given. That's the answer. No, it's not.
No, it won't. What force would be counteracting it falling? Because the magnetic field is coming out of the page, right? Generated by the loop.
Right.
Yeah.
Yes.
Yeah.
Any fluid is coming out of the page.
Uh-huh. Yeah.
And? So?
Oh.
Yeah.
Wait, what are the equations? Hold on. What are the equations?
Equations for
I
what?
don't have any.
I think I have the equations.
For what? Give me a specific
Force,
equation.
force.
Magnetic force?
Oh, Q. V.
Magnetic force?
Yeah.
F B is equal to I L cross B.
Right. Oh, so if B's coming out of the page. No, wait.
Contribute.
Oh, L cross B. Okay. L, I L.
Do I need to know the direction of the
Okay.
force.
Okay. Okay. Got
Do
it.
I need to do anything with the force?
Force equilibrium means zero to net force.
Okay. So
Doesn't it?
we said
Anything in equilibrium means zero net force and zero net torque.
so that equals mg.
That is equal to mg.
Yeah.
Okay, so. Okay, why is it equal to mg?
Okay. Well, you can verify that the force, like, okay, the thing that was confusing me was because I thought since the magnetic field was coming out of the page,
Yes.
that there would be no
this,
there would be no force.
And this is that way. Isn't
But
it?
we have I is this way, IL is that way, and then V is coming out of the page, so the force is off.
Okay, so this one is going to create a magnetic field, right?
I don't know how you do it.
What's the direction of the magnetic field that this wire creates? That this segment of the wire at least creates? What's it going to create? How's the magnetic field? What does it look like? Isn't a wire carrying current?
What?
It's a wire that's carrying current, isn't it?
Yeah.
Okay. What's the magnetic field that it's going to create? Doesn't a wire create a magnetic field? And it has current going through it? Okay.
But didn't we already say that it goes out?
Out
Yeah.
here, right? It goes out here and inward here. Now, the current is going in this wire, it's going in that direction. Okay? What's the direction of the magnetic field?
With the magnetic field constant.
Magnetic force, sorry.
On that,
Yes, on that segment.
so it's like that, down. Isn't it?
Sorry, I, L, E.
Oh, okay. No, never mind.
L, L,
L, yeah.
Uh-huh.
Isn't it?
yes.
Yeah.
And B,
And
which direction is B?
B is there.
B is outside.
Ah,
Out of the
wait.
page. Dots.
Oh,
Dots
okay,
mean out of the
okay.
page.
Yeah.
Out of the page. L, B. L,
Yeah.
B.
Oh, the second one is B?
Second one's B. L,
Yeah, like this.
B.
Why? B. Oh, okay.
L, B.
That way, that way.
Okay.
Okay.
So this is a magnetic force. This is F of B. Okay?
Yeah.
That's F of B, right?
Yeah.
And since it has a linear mass density, surely it has it has a mass.
Okay.
This is weight. Okay? For it to be in equilibrium, like you said,
I don't think so.
IL cross B is equal to mg. Okay, that was.
Oh.
Now you solve it.
Okay,
You have I.
we have
We
I.
can find M. We know G.
We can find G. We know G. G is equal to 9.8.
Yeah. We know L. Don't we?
We don't know L.
Why do you
No.
not give us L?
We only know lambda
Yes.
m. 0.1 grams per meters.
Per meters. Grams.
So you can, that's not.
Meters. Grams. Okay. I mean, L is in meters and mass is in grams. So we don't.
L is in meters and mass is in grams. Okay, we don't know L or M.
Yeah.
We don't know the value of
But
L.
we have this thing.
We know lambda m. What's lambda m?
Something divided by something.
What divided by what? It's linear mass.
Mass divided by length.
Mass divided is equal to mass divided by length. Okay, mass divided by length.
Yeah, and you just put instead of L and then instead of M.
Right. So we want to solve for what are we solving for? B.
E.
Solved it.
IL. Right. So we want we want D.
We want D.
Which is actually we can't go over here. Okay, so we're gonna have to calculate the magnetic field first. Well, we can just assume that we want D now. Okay. So what's the magnetic field gonna be? What's the magnetic field here gonna be? B is equal to. What's the magnetic field from a wire?
U naught I.
ID. D is the thing we want.
Yes.
So,
Yeah.
D is equal to mu naught I over 2 pi D, right? So, and your B is going to be D is equal to mu naught I over 2 pi mg I. Okay.
Yeah.
Lambda m is equal to m over L.
Yeah.
1 over lambda m. 1 over m over L is equal to L over m. L over m. 1 over lambda m. And everything else we have.
That was fun.
That was fun?
Yeah, it was.
Was it?
It was fun.
No, I'm not kidding.
I can hear it in your tone.
No.
It was.
Okay.
Because like it wasn't obvious at first. Like 'cause you only gave us like 2 numbers.
Tension. You remember tension?
Oh boy. Yeah.
Tension of in a while.
Wait. Sure.
Sure. I think we did. Actually, you should remember this because you did it in the lab. The first lab of the semester was tension. This is the ceiling.
Oh, this semester?
Yeah, the semester where you have 2.
Oh, right.
You have 2 charges. It was similar to this.
Remember?
Oh, okay.
It's kind of similar
The
to this, right?
pitfalls.
It was something like this. Is there anything wires? This is 60 degrees.
You can't have infinite wires like that.
Physics, you can't. Okay. 50
What's 50?
grams per meters. Lambda
Of what?
for each one of the wires.
Wow.
So the length of this is 1 meter. The length of this is 1 meter. Okay, so we have a current I that's flowing into the page here, and a current I that's flowing out of the page here. Okay, and what we know is when this current started flowing, this is what happened. It was all balanced at an angle of 60 degrees. Find the value of the current. Actually, here's the solution if you want it. Okay.
No, you can't understand it.
Oh.
See, this is fun because then when we get to the test, it's gonna be like
What do we start with?
it's gonna be like a walk in the park.
Again.
You know everything for you is
Again,
walking
no.
park,
Look,
so.
what happens?
Now they're even more.
Again, what do we say? We said they're balanced. They're in equilibrium. They're in this configuration. You have a 60-degree angle. They're in equilibrium. What does equilibrium mean?
The forces are equal.
Forces are equal. So
So we need to
net
do-
of forces is 0. The total sum of forces on the thing is 0 when it's in equilibrium. Okay?
Can we draw the forces?
We can't draw the forces. What are the forces? You tell me. What are the forces on each one?
I mean, it
So
goes down.
what goes down?
Force.
Which force? There are multiple forces. There's gonna have to be more than one force if it's gonna be in equilibrium, right?
Yeah.
Okay.
Of weight, and then the opposite one.
This is weight
Yeah.
of each one of them. Weight is gonna be the same for each one because they're the same weight.
But because they're at angle, then the tension will go that way.
The what? The tension? Yeah, the tension is gonna go. The tension is always in the wire, right? This is T and T,
Yeah.
right? Okay.
Is there something else?
There should be, shouldn't it? This is not gonna balance out.
Yeah.
For it to be 0, all the forces that are acting on it have to be 0. And there's no way these are going to ever add up to 0.
Okay, another one should go the other way. There.
Should go
No, there.
this way? Okay. What is this force though?
I don't know.
What are the possible forces in this configuration?
What?
Okay, you have 2 wires.
Yeah.
Do you remember? They repel or they...
Oh, okay. They repel. These two don't like each other.
Okay, after repel. So, they're on the same line.
Yeah.
So this is the magnetic force. Okay. Now what? Next step. What's the next step?
So they all equal to
All are equal to 0. Okay. How do we add vectors? For them to be 0, that means the sum of all of them has to be 0, right? Well, how do we add
I mean,
vectors?
that one and that one goes this way.
Very well.
These two?
No, I'm not saying you're wrong, I'm just saying. This one and this one?
Yeah.
What about
That way?
this way? Yeah, well, this one and this one. So, I mean, the sum of these two has to be in this direction
Yeah.
for it to cancel out with that one, right? But I mean, the easiest way to add vectors is to add the x components together and add the y components together. Because every vector in 2 dimensions has an x component and a y component, right? If this is v of x, and this is v of y, okay? So this vector is already in its x component form. This is already its y component, and this one we need to put it into x component and y component.
Okay.
Right? Okay, how do we put this vector into x component? What component?
So for x component, it's just the cosine.
Right? Cosine which angle?
60.
60. T cosine equals 60. So this is tx. Tx is equal to t cosine 60.
And we can add it to FB, but
Right.
we can't add it to
Tx plus fb is equal to
what?
what? What is it equal to?
0.
0. Right? So you have to add up to 0.
Okay, and then F, V, W, whatever.
Yeah, w. W is equal to, or w plus, let's say w
Yeah,
plus,
W plus Ty is T sine.
ty equal to
So 0
0. So, and ty is, the ty is equal to t
sine.
sine 60. Right? Okay. So, we have t cosine 60 is equal to
Negative. What is the
magnetic force, Fb, and t sine 60 is equal to weight.
Oh, and you're asking for tension, right?
And we're asking for
What's right here? To
the
find
current.
I's.
Yeah, find how much current we have to have for this to be stable.
Okay.
Not really stable, but yeah, also unstable. So, what are we doing from here?
What is the formula for force? Oh, because I will be there, right?
Because what?
I mean, that's how we're going to find.
So it's the same formula that we used a second ago. Actually, let's have a formula so we don't have to keep on. Oops. Okay, so if you have 2 wires, the opposite direction, we know that they're either depending on the direction of the current, they're either going to repel each other or attract each other. So let's say this one has a current I1, this one has a current I2, and let's say we want the force at wire 2, this is wire 2, this one. We want the force at wire 2 due to wire 1. F is going to be IL cross V, right?
Okay.
I don't know if these are up this in the 3 lectures or not, I'm not sure. But, well, that's going to be I. What's the direction of the magnetic field?
Which of which one?
Of this one. Around this wire.
Wait.
I.
Okay, hold on. Wait, because
This
they
is-
repel,
this-
right?
Yeah.
So that goes here. So we have
That's the
this.
force. That's the magnetic force. We want the magnetic field.
Right.
So,
But we know the direction of current and the force.
Well, yeah, okay, you can do that.
No?
No, you can do that.
Okay, so this is I and this is F. So that way.
Here. Something like that.
Then that way.
So if you're going to do that one, you're going to say, okay, they repel each other, right? So the force on this one is going to be this one, so it's going to point that direction. That's force.
Yeah,
right?
that one.
Right, this is the force. And this was direction of I. So it's in this direction, right?
Yeah.
Okay.
I did this.
And where's your...
The second one, right?
Yeah.
That
Yeah,
way.
second
To
one.
me.
No.
What?
It's like this. It's not like this. Like this.
But force is going to me.
Yeah, but I mean, this is your current, right? This is your current pointing downward, right?
Yeah. Oh,
This
okay,
is the B. We don't know where it is yet,
We can't.
right? We don't know where this is yet, but we know where this is. This is the force.
And it is.
The force is in that direction. The repellent.
Okay,
right?
this way.
So it's pointing
Okay,
inward,
okay.
right? So it's pointing into the page. So they're pointing into the page. That's not into the page. Why am I always drawing opposite signs?
Yeah, I also have this problem. Today I was at chemistry.
I never had this problem before, actually.
I have it in chemistry though.
I'm dyslexic, apparently. But anyway, this is L. So, I mean, the point of it is that L and B are perpendicular, right? Because the length is in that direction and B is in that direction, so they're perpendicular. It's 90 degrees, right? So ILB. I, L, what's B? B is due to the other wire, right? The magnetic field here is due to this wire, right?
Yeah.
So B is just mu naught I over 2 pi D, D being the distance between them. So the force from one wire onto the other is just, this is I2, I1. It's just I1, I2, mu naught, times L over 2 pi D. L being the
Okay. And I have another question. In
Just
our
a-
case, the I is the same, right?
Hmm?
Our I is the same here. Okay. Yeah.
Okay,
Okay.
I is the same.
Yeah.
Now, we just
So
derive.
cosine of 60 and sine of 60, we know it.
Yeah, we know sine 60, we know cosine 60, we don't know T, we don't know alpha B yet.
But okay.
And we
So,
don't know
but it's T because T and T is the same, right?
T and T are the same.
So we can just divide it
We
by
can divide
sine
them.
60
That's one way to do it.
and then we can.
Let's divide.
Equal.
Let's divide this over that, so we can get a tangent.
Okay.
Tangent of 60 is equal to W over. Actually, so it was originally negative, right? But you can deal with the magnitudes. You don't have to deal with directions.
Okay.
You can just say magnitude of this should be equal to magnitude of that. Magnitude of this should be equal to magnitude of that. Okay. So that we just say tan of 60 is equal to the magnitude of W over the magnitude of F of B. Okay.
And we know F equals.
It's tan of 60 is equal to weight is mg over
I squared, yeah.
F of B is I squared,
L mu naught,
L mu naught
and then in the.
over.
I mean, you can write it up there. But
Just do that directly then. Times 2 pi D, right?
yeah.
Okay. Let me solve this for I.
Yeah.
Right. Solve for I squared. Well, I is just going to be equal to root of mg times 2 pi d over n 60
L
L
mu naught.
mu naught.
Do we know L and D?
We know this thing, and we know that. We know lambda m. We also know that the length of these is 1 meter each. So what's this distance? 1 meter. So that's d is equal to 1 meters, right? Root of g 9.81 times 2 pi times d is 1 meters.
We can find mass.
We can find mass. mass, right? We can't find mass, we can find mass over length. Right?
Yeah.
We know this quantity here, right?
Yeah.
Mass over length is 1 down.
Mm-hmm.
Times 2 pi. Understand something? Was it 4? You know, it's 4 pi. 4 pi, right?
Yeah.
4 pi.
4 pi, that's the next one.
The -7. Times root 50 root 3. That's it. This is supposed to be a nice number. Because, I mean, I assume it's a nice number because otherwise they wouldn't have given us this. Oh, well, we...
Times cancel.
It was 10 to 60.
But 10 of 60 has root 3 in it, so... But yeah, I mean, I think in high school, well, I mean, this book doesn't usually uses G is equal to 10.
10.
It's not approximate. But whatever, just kind of feel. Rough approximation.
Nice.
Yeah, I had another one that was full of harder problems, but I didn't get it to spec. It's back home. Unfortunate. Actually, the one we just did.
Do you write answers in? Oh my God, you don't even. I thought at least numbers would be like similar.
No, we have different numbers too.
Holy shit.
Everything's different.
You have different variable numbers?
Well, yeah, they're in there. It's the same. Pi. You can recognize pi.
Aw.
You can recognize pi and maybe
Mu
is the same,
Alright.
but the not is on the other side of the cell.
Why?
Because it's mu not. It's not mu not.
Was it difficult? Hold on. In your high school, did you learn English or no?
Yes, I started speaking English around the same time I started speaking Arabic
Okay.
because I was born here.